Progress.
Not hybrid, so not gas or metal deposition, so real in the term sense of scalable for capacity and power. So let's have a conversation about this. Okay, so we are coming to Lily from Cougar Creek Technologies, and you're talking about iron chromium complex redox flow batteries. And the stage is yours.
Okay, thank you for introduction and thank you for the opportunity from the organizer. We are a company located in Seattle, Washington State, USA. We are a technology development company. We believe in invented in USA and made with local. And that's our business strategy. And also we believe in communications and with other partners together. So also for the large scale, practical, long duration redox flow battery, we believe in these three properties. The number one is true redox flow battery. Number two is symmetrical battery system. So we don't trust the membrane can separate the two electrolyte. And also the last thing is you have to use earth abundant material, cost is low enough to support the terawatt hour projects. So that's the three things. So with these three criteria, seems like nothing we can do except this one. That's the famous Larry Solar from NASA. And he's invented this technology about 50 years ago. Actually, this one never been successfully demonstrated in the past years, although many companies try this one. So major issue with this one is the Chromium 2 and Chromium 3 electrochemically not very active, and then generate the hydrogen, capacity decay, then system just is dead. So why we are working on this one is we make two major development, improvement in this system. So the number one is we make a complex, near neutral complex system. We put a nitrogen containing ligands to complex the chromium. So we make that complex and then largely improve the electrochemical reactivity. So in order to make that complex, put the nitrogen ligands onto the chromium cations, you have to reduce the proton concentration in the solution, which is not a bad thing. And the second thing is, after you reduce the proton concentration, you cannot use ionic, like a Neptune membrane anymore. You have to use something, can use transport all the ions in the solution. Then we get a separator, which is much lower cost. So with this nitrogen containing complex, we can reduce the hydrogen generation rate from like about 1% original traditional system to 0.05%. So the hydrogen generation largely reduced, but it's still too much for a large system to be sustainably operational in the long term. Say, for example, for a 2.5 megawatt hour system, if we run like every 6 months, half a year, we need about 10 cubic meter kind of iron electrolyte, iron 2 and proton electrolyte to regenerate this hydrogen-related iron 3, and then we make another 10 cubic meter electrolyte, iron 3 electrolyte waste. So that seems like still too much. And then come our another invention is we pretty much using the positive side of vanadium flow battery, the vanadium 4 and vanadium 5. So with that one, we can reduce the iron 3 back to iron 2 and put the proton into this side. And also we get the vanadium 5 and the proton, which is very, very good, efficient oxidizer. Then we put some kind of reductant into that solution, just like for chemical reaction. Then we reduce the whole thing, vanadium 5 back to 4, then we can restart everything again. So with this one, we can, with very minimal cost for every half year for this 2.5 megawatt hour system. Actually, one of these, 100 kilowatt, 200 kilowatt hour vanadium flow battery unit can support half gigawatt hour system annually. So, so that's the two major inventions we make. Then that's why we think we are ready to commercialize this historical iron chrome system. This is some data. Last year I presented hundreds of cycles for single stack. And this is 6 30-cell stacks, which will be our modular data. So this is a whole modular charge-discharge curve. And then this is an individual stack, the voltage charge-discharge. So this is so an example. Okay, now let's go to the major part of the talk. Let's talk about the money. Yeah, let's talk flow battery, let's talk money. In the past year, the major work was on how to reduce the cost of this system. Last year, I presented 2 megawatt hour demonstration project. I used the chromium chloride salt. So the theoretically per kilowatt, $72 per kilowatt hour, but there's just not enough material. You cannot use all the chromium chloride in the market for the energy storage. So this year, we're mostly working on this two system. We already developed the process to use iron chrome metal alloy and the chromate ore last year. And this year, we try to see how we can make this commercially, ready for the electrolyte. Again, we are working mostly with our supply chain, our vendors, Liyu Communications. We identified, there's a huge kind of an industry that's for the waste acid treatment industry. Once you wash the stainless steel to treatment the surface, it generates a lot of waste acid solution, and this solution will be collected by this kind of iron chloride producer, and then they make either to the iron chloride solution, or they can make the high purity iron chloride salt. So that one, they already have all the equipment, all the process, even for the impurity removal. So we identified 2 vendors already, and they use this iron chrome alloy metal, and then produce the electrolyte here, and also produce the mixed crystals. Each of them have a gigawatt hour electrolyte production capacity per year. So this is one good thing. Actually, we can do even better because the iron chrome metal alloy, it seems like, when you this iron chrome ore, when you do this one, just mix with carbon, you can reduce that. And all the way, when you go to the metal alloy, a lot of steps, only 1/3 of the step is kind of useful in terms of electrolyte manufacturing. So we are working with our licensees and also other partners, try to directly using the iron chrome ore to make this thing. So if we can use the iron chrome ore, you see the price can be even lower, couple dollars in terms of per kilowatt hour. So that's the electrolyte part, and then we are also working with many vendors on the stack part. So the first thing, as I mentioned, we reduce the hydrogen concentration in the electrolyte. We can use HDPE porous separator. We already identified the suppliers about $1.5 per square meter, and they have millions square meter production capacity per year. Bipolar plate, $10 per square meter. Carbon fiber, $10 per square meter. Carbon fiber, this is not graphite fiber because I use iron 2 and iron 3, so the oxidation voltage is too low, so we can survive with the carbon fiber. So then, from the high temperature insulation industry, this price is very reasonable. And other things, and the current collector is copper. Based on Adam's talk today, I think I can reduce this cost, maybe cut by half. So anyway, in terms of material cost for a stack with 10 kilowatt, 10 kilowatt standard rated power, so total cost about $1,000. So which means $100 per kilowatt, and if for a 10-hour system, that's $10 per kilowatt hour. So that's the material cost. Then let's see the manufacturer. So we are also identified the stack vendor. They are using the all automatic welded the stack. So this is a video. I don't know how can I get this one. This means we design a single cell, like this is single cell. So we pre-make a single cell. This cell can put together over here and then do all laser welding and then make this stack. This is 2,800 square centimeter stack with 30 cell. So 60 cell, this is half cell. So 60 cell is 10 kilowatt rated power. So that's the stack part. Oh, it's, yeah, see? Thank you. Yeah, I'm not cheating. So with that one, seems we're ready to build a building block based on the technology. We have electrolyte, we have stack now. Then we design the system, a building block 2.5 megawatt hour system. The rated power is 250 kilowatt. The maximum power is 500 kilowatt. So that's, for you, because that's the desired ratio. You have to give the higher power, so then you can do like short-term charge or discharge in the long-term duration. And this is the design, and this gives you more design details. The design are already finished. So it's not fully modularized. We only modularize the stack part and the electrical control part. Also some of the pipe and the pumps, it's all separate. The tank is very critical. All these things designed based on 10 cubic meter tanks. And each one pair of 10 cubic meter tanks work with 3 stacks. And this is the thing we start with. So with that one, I would think the cost at 100 megawatt hour scale, we can go all the way to $120 per kilowatt hour, including EPC. And with gigawatt hour scale, we can go to 60. And one last one is, seems too good to be true. Now we are working with a lot of the demonstrators, and we have the concept. I'm going to one of them right after this meeting. Start with 2.5 demonstrator, 2.5 megawatt demonstrator, and then if successful, we'll move to 500 megawatt hour. So, thank you for your attention.
Thank you. Applause. And you can find Liu's paper on page 70. So, and of course, with real flow batteries, I meant, please stay up. I meant, of course, classical flow batteries. Yeah. Okay. So, I don't want to judge his technologies. No.